It's really great to be here. I really enjoy coming to these kinds of workshops where you have people coming from broad backgrounds, different kinds of backgrounds. And in this talk, I'm going to start off with a little bit of a high-level introduction that I think everybody can relate to. And then I'm going to go into a little bit of a CS motivation. You know, that's my background. I come from machine learning, computer science, and so on. But then the core of my talk, I'm actually going to be talking about some very new results that we have that I think span kind of statistics, large-scale optimization, mathematical optimization, and then some other ideas from computer science. So I'm particularly excited to present it to this audience. And I'd love to, you know, I'll do a short version here, but I'd love to talk to people afterwards in more detail if they see connections. And I think following up on Peter, I'm going to relate to some of the last questions about structure in the data. And I'm actually going to argue part of what's different about big data is that most of the data doesn't start off originally in this nice, clean matrix table form. And it doesn't even start off as, you know, collections of little trees. I mean, sometimes it does. Sometimes in biological data or natural language processing, you can think of parsers of sentences and so on. But usually, what it starts off as is this kind of giant graph-like thing. And here I'm using different shapes of nodes and think of different kinds of edges. And even the fact that I drew it as like this finite thing is already a huge approximation, because really it's kind of infinite, because you can keep joining on things and bringing in more data, and you know how you think about how you do that is really important, both from a viz perspective, but also from a machine learning and statistical modeling and optimization perspective. And you know, my cartoon of this is right now what we tend to do as data scientists is we take this big graph data and we flatten it into a table, or I like Peter's term, smush it or smash it into a table. And there's a lot of subtleties in what happens in this process. From a statistical perspective, I think the thing that's interesting is oftentimes when people flatten it in this way, they then make independence assumptions between the rows, which maybe are appropriate, but maybe not. And so really kind of thinking through, by the fact you flattened in a particular way, was that the right way to factor your data and make the parameterization or the independence assumptions? But then also just from a feature engineering perspective, you know, there was a lot of information about how things were linked and what were attributes and what were relations that are potentially lost here. And how do we have methods that kind of keep track of that, so at least you could recreate it, even if you still want to then apply your method that works on the tabular form. And so I really think that we need machine learning methods which have some sort of declarative way of talking about that structure. So whether that's coming from using your database knowledge, your schema knowledge for representing features and also representing models, or your AI knowledge representation, whatever, I think that's important. Then being able to say, okay, I'm going to model dependencies, I'm going to make joint inferences, and then finally having a model that is generalizable in some way so that you have a template for the model. And I'm going to unpack these in a little bit, so if they don't mean anything to you right now, hopefully by the end of the talk they will mean something to you. And I'm going to talk about a particular method that's being developed in my group, but I very much want to say it builds on a whole collection of methods that people have been trying kind of typically, but not always, on the edge between kind of machine learning and AI and computer science, where they're trying to develop probabilistic programming languages, but then that scale to these kind of collective inference problems. And I'm going to describe one that I think kind of builds on the best of many of these, but if you're interested in more about them, this is a longer tutorial that kind of goes into more details about these. So the system that I'm going to talk about, we call it PSL for probabilistic soft logic. It is open source. There's a bunch of tutorials and so on available here, some videos. And I do want to call out Steve Bach is one of the key contributors behind this, and in particular the mathematical result that I'm going to show in just a few minutes. He's currently a postdoc at Stanford working with Chris Ray's group. And then Jay Pujara is one of the key students currently working on it. He's a postdoc in my group. He's done a lot of cool work on applying PSL for knowledge graphs, so if that's something you're interested in. So what is PSL? It's basically a probabilistic programming language for collective reasoning. And I'm going to say what collective reasoning is, but just think of it as joint reasoning. We're going to have predicates which can represent either attribute values or else the relations, so the links or the ties. We're going to have rules that capture probabilistic and dependencies and logical dependencies and other useful things like aggregates and so on. A PSL program is basically a collection of rules together with some input data, and then I'm going to show you what the PSL program defines. It defines a probability distribution, and I'm going to show how we can find the most probable assignment for the unknown variables in this probability distribution. The key thing, you know, if you've seen any of these kinds of languages before, the key thing that makes it different and the key thing that is going to end up being the thing that helps it to scale is that the random variables, rather than being combinatorial, so rather than being 0 or 1, so logical variables, they're going to be continuous valued between 0 and 1. And I'm going to show you in a few minutes 3 very elegant mathematical approaches that end up getting you to this solution. But before that, let me give some motivation for the kinds of problems we might want to solve using this kind of language. So the first one is we have some network and we're trying to label the nodes in the network. And so I'm going to give toy examples of a few of these things where suppose I want to figure out the political persuasion of an individual in the network. Okay, so I'm definitely going to use any local information that I have about the individual. So I'm going to look at, you know, oh, did they contribute to some campaigns? Then I'm going to have this thing that looks like a rule. But so how many of you are kind of logic programmer types or data log types? How many know something about data log? Okay, good. Because usually in a CS audience, I have to say, no, 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 no. Don't think of it like a logic program. But you guys won't have this issue. Instead, what you should think about it as is you should think about it as a potential function. And this potential function, this one is a super easy one. It's just a node potential. So it's something that's gonna, we'll see, say something about the likely labels for a node based on some attributes of the node. Then we can look at other kind of local information, so we can look at their status updates, their tweets, and you know, we can do this kind of trivial NLP text processing. We can look for loaded terms. If they use them, we can say they're more likely to vote for something. So all of that is pretty straightforward. Now what we want to do is take into account more of the network structure. So in this case, I have some sort of social network. Some of the nodes are labeled. But I certainly want to be able to say the kind of common things, like saying, okay, if my friend votes for a particular party, I'm a little bit more likely to vote for that party. And if my spouse votes for a party, maybe I'm even more likely to vote for that party. And I want to do that, but I want to do that in a way that I can then go, and for the unlabeled nodes here, I can label them in a way where I don't make their predictions independent of each other. I collectively, for all of the unknowns, find the most likely joint assignment of all of the labels. And so that's, again, it's kind of an easy idea, but that's one of the things that PSL is very much geared towards. And you can do this for richer kinds of problems than just the node labeling problem. The node labeling problem is the easiest problem, but where, for example, I'm trying to figure out an organization hierarchy and figure out who reports to who. Well, I could do something that starts off by saying, okay, I have certain kinds of emails, and the kinds of emails can indicate whether they're a deadline email maybe or a social email. And then I can say something like, oh, well, if someone sends certain kinds of emails, then the kind of relationship between them is more likely to be a certain kind. And then I can do things like, say, kind of a definitional constraint that says, well, if A is the supervisor of B and the supervisor of C, then B and C are colleagues. So I can include these kinds of semantic things where I take some links that I've observed and infer other kinds of semantic relationships. And then the other thing that we tend to do a lot is we do a lot with entity resolution. So this is a data alignment kind of problem where, if I have two references, I'm trying to figure out, are they referring to the same underlying individual? Then I want to do something where I have dependencies that use whatever string similarity you want to among the references. But then we also want to use the graph structure and the collective reasoning to do things like say, okay, well, not only if their names are similar, they should be the same, but if they have similar friends, then they should be the same. And then on top of it, oftentimes you want a kind of transitive closure kind of principle where if A is the same as B, B is the same as C, then A and C should be the same. And I've written this as a hard constraint. Usually you actually don't want it to be a hard constraint. You want it to be something that just has high confidence. So at this point, I've tried to give you cartoon examples of some useful flavors of PSL programs. But what's interesting is we're going to make all of this tractable by mapping these things that look like rules into convex functions and then show how to combine them. And what I think is super exciting is except for, oh, that's not good. Three different semantics that lead to the same optimization. And I'm going to go into more detail on the first one, the randomized algorithms approach to setting up this problem as an efficient inference problem. So how does PSL work? I'm going to go back, actually, even though I said we're going to end up having continuous values for the random variables, I'm actually right now going to go back to discrete land and combinatorics, where for now, the variables, the x's, are going to be 0, 1. And to simplify things, think of these PSL rules as they're weighted rules. I'll tell you how these work in a sec. But they're simple rules where I have a conjunction of variables that are in the body, a disjunction in the head, and then the variables can be negated or non-negated, but I am going to keep track of the set of variables that were in the body versus in the head. And I'm going to do a standard thing of rewriting them as just an equivalent disjunction over all of these variables. So nothing magic here, a very common thing to do. And then what I'm going to do is I'm going to define an energy function that will give me a probability for each assignment of the random variables. And I'm going to make this proportional to the weights of the sums over all of the rules instantiated on the data over this disjunction. So again, this is a simple way of defining a distribution over these states of the variables. And now I'm going to define the map inference problem as find me the argmax for these. What's the most probable values? Cool. And so does this look familiar to anybody? All my CS people should be saying, I know this problem. This is MaxSat. And, you know, MaxSat is a well-known combinatorial problem, and it's a well-known combinatorial problem that's really hard to solve. And so, you know, I've just done all this hand waving to give you an NP-hard problem to solve for the system. So that's no good. So now I'm going to start making the switch. And instead of viewing this as these combinatorial values between 0 and 1, I'm going to now change the interpretation to a rounding probability. So the probability that I round up to 1 or down to 0. And in that case, I can define the expected score of a clause as being, you know, the probability that at least one of those terms in the disjunction ends up being true. I can rewrite it in this simple way. And then, you know, I can rewrite that exponent as this sum. And, you know, I can say, okay, let's try and solve this instead. Unfortunately, this still ends up being highly non-convex due to the product, so I haven't gotten that far. So the nice thing that I can do is I can use this well-known result of Goemans and Williams for bounding this, and this bound gives two nice properties. So one nice property is it ends up giving me a convex optimization, and then on top of it, it actually gives me a guarantee on the solution quality. And so those two things together are terrific. Now to make it scalable, we can exploit the structure of the optimization even more, because there's really a fine-grained structure in these things. And I can look at each of these kind of potentials, look at the graph structure, and make use of a variety of optimization techniques, but in particular the one that we make use of is ADMM, a consensus optimization that, you know, we have to do a little bit of work to show that we can solve these efficiently. And we get something where we've gone from something that started off as a combinatorial problem. You know, we can solve it with off-the-shelf interior point method, or we can use ADMM. This is a cartoon here's something on real data that just shows these two lines where I get these speed ups where I'm taking things that take hours or days and get them to seconds or minutes. So this is one interpretation. The second interpretation that is very nice is a connection between this and graphical models, where in graphical models there's a lot of work in these kind of local consistency relaxations. But the challenge is most of those techniques had no guarantees on approximation quality. So it turns out if one does some math and thinks of this now as a giant graphical model directly, looks at the local node potentials, the marginals, and makes them consistent with the node potentials, edge potentials, and any other potentials, the cool thing is doing a little bit of work and manipulation, you get out this optimization. It turns out that exactly mirrors the optimization that we got for the randomized algorithm. So this is very cool. And then the third interpretation, and actually the one that we started off with, was we wanted to reason about similarities. And so we were actually in the setting where we were trying to map ontologies and say, okay, you know, which concepts map to each other, which relations and attributes and instances. And we started off doing this in this combinatorial way with this kind of 0, 1. But then we converted it, because it made sense in this domain, to say similar, to what extent, between 0 and 1. And so then what these rules became were these ways of combining together these truth values that are between 0 and 1. Those can be interpreted as degree of truth. They could be interpreted as similarities. And again, we chose a particular well-known approach for converting these kind of logical operations to values when they're between 0 and 1. And it turns out the optimization that you get when you do this is the following. And if you kind of squint at this, this actually has the same form as the other two. So we've been able to say that, you know, all of these end up being the same, which is exciting. Then we've extended this to allow for linear constraints, hard constraints, and so on in this form. And a question becomes, okay, well, does it work? You know, this is all nice math. I'm going to very, very quickly show you some results. Here we're comparing a continuous HL-MRF with a discrete. We're doing better in terms of performance for a node labeling problem and for a link prediction problem. The biggest thing, though, is the speed. We're getting orders of magnitude speed up even on these small problems. A couple other settings where we're comparing to state-of-the-art techniques for image reconstruction, for activity recognition in video, and then some biological data, drug target prediction, and we're doing very well. We have a lot of other applications that I'm happy to talk about. We do a lot of stuff in computational social science, social media kind of data, and we also do a lot in information integration and extraction as well, which I was going to show you a little bit about knowledge graphs, but I'm going to click through that. We do it really fast. So PSL is nice, it's open source, it's scalable, but the key thing is I think it gets those three things that I really think are needed for methods now, that we have some way of declaratively talking about the features and the kind of dependence between the attributes, that we have a way of doing collective inference and the way that we can have these kind of patterns. So these rules give you templates that are potential functions that get repeated over and over in the model. I didn't get to talk about it, but we also do weight learning, and we also do some work in latent variables. Latent variables, of course, breaks the convexity, but still we've been able to do some nice things there. And I think it's a really interesting fit for these kind of data integration kinds of problems, but also structure prediction problems, whether it's for natural language, vision, or biological data, and so on, where you have some structure. But these results are really fresh. I think there's a lot more that one can do, and I think this is an exciting area. So, thanks.